For decades, if you saw an EMD locomotive, you knew what was inside. An EMD engine, the 567, the 645, the 710. These were the prime movers that defined American railroading. Then, in 2015, something unexpected rolled out of Progress Rail's factory in Muncie, Indiana. It wore the EMD badge. It carried the design legacy of Electromotive, but under the hood sat a Caterpillar C175, a 20-cylinder engine built for mining trucks and industrial generators, not locomotives. This is the EMD F125, and it represents one of the most radical departures from tradition in modern American locomotive history. It wasn't built to haul freight across mountain grades or pull intermodal trains at 70 miles per hour. It was built to solve a very specific problem. How do you design a passenger locomotive that meets federal crash standards, satisfies EPA Tier 4 emissions requirements, and delivers the rapid acceleration needed for commuter service, all while traditional locomotive engineering was running into regulatory dead ends? The answer involved abandoning decades of EMD engine heritage, adopting crash energy management principles from European rail safety standards, and creating a locomotive that would become both a technical achievement and a cautionary tale about the challenges of innovation in American rail transit. Before we continue, if you think our content is unique and informative, please leave a like and subscribe. It really helps support the channel. Also, make sure to share the video with other train fanatics out there. By 2008, commuter rail agencies across the United States were facing a convergence of problems. The locomotives they relied on, mostly EMD F59 PHIs and F59 PHs built in the 1990s, were aging out. More critically, they were becoming illegal to build. The Environmental Protection Agency's Tier 4 emission standards, finalized in 2008 and phased in through 2015, set strict limits on nitrogen oxides and particulate matter from diesel engines. These weren't incremental improvements over Tier 3. They required fundamental redesigns of combustion systems, after-treatment hardware, and engine management software. For locomotive manufacturers, Tier 4 meant that engines designed in the 1960s and refined through the 1990s could no longer be produced without massive modifications. At the same time, the Federal Railroad Administration was implementing new crash energy management standards. These regulations, influenced by investigations into several high-profile collisions, required passenger locomotives to incorporate sacrificial crush zones, anti-climber mechanisms, and reinforced operator cabs, designed to protect crews during frontal impacts. The traditional carbody design, essentially a structural frame with sheet metal cladding, was no longer sufficient. Metrolink, the commuter rail agency serving Los Angeles and the surrounding counties, found itself at the center of these pressures. In 2008, a Metrolink train collided with a Union Pacific freight train in Chatsworth, California, killing 25 people. The subsequent investigation revealed that the locomotive's cab structure provided inadequate protection during the collision. Metrolink faced both public pressure and regulatory mandates to improve safety. The agency needed new locomotives, but the requirements were daunting. Tier 4 compliance, crash energy management, higher acceleration rates for dense urban service, and reliable head-end power systems capable of supporting long trains in extreme heat. EMD, Siemens, and Motive Power Industries all submitted proposals. EMD's offering was the most ambitious, a completely new locomotive, not a modification of existing designs. But there was a problem. EMD's 710 engine, the backbone of their locomotive production since 1984, couldn't meet Tier 4 without adding so much after-treatment equipment that the locomotive would become impractically heavy and complex. The company had attempted to develop a successor, the 265H, a 16-cylinder H configuration engine intended to replace the 710. That project failed. By 2010, EMD was owned by Caterpillar, and the decision was made to look outside the company's traditional engine lineup. The Caterpillar C175-20 is not a locomotive engine. It's a 20-cylinder V-configuration prime mover designed for off-highway mining trucks, marine propulsion, and stationary power generation. In mining applications, it powers haul trucks carrying hundreds of tons of ore through desert heat and high-altitude conditions. In marine installations, it runs continuously for months at variable loads. Caterpillar had already developed a Tier 4 compliant version for the U.S. market, incorporating advanced fuel injection, variable valve timing, and optimized combustion chamber geometry to reduce emissions without resorting to excessive exhaust gas recirculation. For EMD's purposes, the C175 offered several advantages. First, it was already certified to meet Tier 4 standards, eliminating years of development time and regulatory approval processes. Second, at 4,400 horsepower, it provided substantially more power than the 3,200 horsepower 710G3C used in previous EMD passenger locomotives. This extra power would allow the F125 to accelerate heavier trains more quickly, critical for commuter service where schedule adherence depends on rapid station departures. Third, the C175's physical dimensions were surprisingly compact for its output. The engine's bore and stroke, 170 mm by 215 mm, created a relatively short, wide power plant that could fit within a locomotive underframe without requiring an excessively long carbody. Fourth, the engine's modular cylinder head design meant that individual cylinders could be serviced or replaced without disassembling the entire engine, potentially reducing maintenance downtime. The decision to use the C175 was not without risks. Locomotive engines must withstand constant load cycling, extreme vibration, and rapid throttle changes, operating conditions different from the steady-state loads, typical in mining or marine applications. The engine would need modified mounting systems to isolate locomotive frame vibration, revised cooling systems to handle commuter service duty cycles, and entirely new control interfaces to communicate with EMD's locomotive management software. Caterpillar and EMD engineers spent 2 years adapting the C175 for rail service. The engine's turbochargers were retuned for faster transient response during acceleration. The electronic control module was reprogrammed to interface with EMD's traction control systems. A new SCR, selective catalytic reduction, system was designed to inject diesel exhaust fluid into the exhaust stream, converting nitrogen oxides into nitrogen and water vapor. The entire assembly, including aftertreatment, weighed approximately 36,000 pounds, comparable to the 710 it was replacing despite the significant increase in power output. What emerged was one of the most powerful single-engine passenger diesels ever built for North American service. The F125's 4,400 horsepower output exceeded that of any previous EMD passenger locomotive and matched the output of many heavy freight units. This power would prove essential for moving 6-car bi-level commuter trains through Los Angeles basin traffic patterns, where rapid acceleration between closely spaced stations determines whether trains can maintain schedule reliability. The F125's carbody structure represents a fundamental departure from traditional locomotive design. Where earlier passenger diesels used a relatively simple structural frame with non-structural outer panels, the F125 incorporates crash energy management principles throughout its architecture. The locomotive's front end features a sacrificial crush zone designed to deform in a controlled manner during a collision. This zone absorbs impact energy progressively, extending the deceleration time and reducing peak forces transmitted to the operator cab. Behind this sacrificial structure sits an anti-climber, a rigid beam positioned to engage with similar structures on an impacting locomotive or rail car, preventing one vehicle from riding up and over the other. The operator cab itself is a reinforced survival cell, with structural members designed to maintain cabin integrity even if the forward sections of the locomotive are severely damaged. These safety features add weight. The F125 weighs 280,000 pounds. Approximately 15,000 pounds more than an F59 PHI, but Metrolink and the FRA deemed the safety improvements essential after the Chatsworth collision. The locomotive's cooling system is one of its most distinctive engineering features. The C175 generates substantially more waste heat than the 710 it replaced, and Los Angeles summer temperatures frequently exceed 100 degrees Fahrenheit. EMD engineers designed a split cooling system with 2 large radiator sections mounted on the old locomotive's roof. These radiators are fed by hydraulic drive cooling fans that can vary their speed based on coolant temperature, reducing parasitic power losses during cool weather operation, while providing maximum cooling capacity during extreme heat. The roof-mounted design serves multiple purposes. It removes heat sources from the engine room, improving working conditions for maintenance personnel. It allows for larger radiator surface area than would be possible with traditional side-mounted radiators. And it simplifies airflow management. Hot air exhausts directly upward rather than creating turbulent zones around the locomotive's sides. The F125's head-end power system represents another significant engineering improvement. Previous EMD passenger locomotives used alternators driven directly by the prime mover to generate electricity for passenger car heating, cooling, and lighting. This meant that HEP output was tied to engine speed, and any prime mover failure would immediately cut power to the entire train. The F125 uses a separate 1,000 kilowatt inverter system. The prime mover drives the main alternator, which supplies power to both the traction inverters and the HIP inverter. This arrangement allows independent control of traction power and HIP output. If traction power fails, the HIP system can continue operating, keeping passenger car climate control and lighting functional. For a commuter agency operating in Los Angeles summer heat, this redundancy is critical. A disabled locomotive can maintain passenger comfort even while waiting for rescue. The traction system itself uses modern IGBT, insulated gate bipolar transistor, inverters to convert the main alternator's three-phase AC output into variable frequency AC for the traction motors. These inverters allow precise control of motor speed and torque, essential for the rapid acceleration and smooth deceleration required in commuter service. The F125's traction motors are designed for high starting tractive effort. The locomotive can accelerate a 6-car bi-level train from rest to 50 miles per hour in less than 90 seconds, matching or exceeding the performance of electric multiple units on similar commuter routes. Unusually for a diesel locomotive, the F125 incorporates dynamic braking with regenerative capability. During braking, the traction motors act as generators, converting the train's kinetic energy into electricity. In a purely dynamic braking system, this electricity is dissipated as heat through resistor grids. The F125 system can feed some of this energy back to the HEP inverter, reducing fuel consumption during deceleration. The regenerative capacity is modest. The system can absorb all the braking energy from a full train, but it represents a step toward more efficient commuter rail operations. The locomotive's electronic architecture is entirely modular. Control cabinets are designed as line-replaceable units. Entire modules can be removed and replaced in under 2 hours without extensive rewiring. This design philosophy reflects lessons learned from decades of locomotive maintenance. Complex electronic systems fail, and the priority is minimizing repair time rather than field repairing individual components. Metrolink's maintenance facilities can swap a failed inverter cabinet and send the defective unit to a depot-level repair facility while returning the locomotive to service the same day. The F125's development was far from smooth. Metrolink ordered 21 units in 2013, with deliveries scheduled to begin in 2015. The first locomotives arrived on schedule, but they immediately encountered problems that would delay full deployment for more than 2 years. The primary issues were electronic. The F125 integrated systems from multiple manufacturers, EMD's locomotive control software, Caterpillar's engine management system, traction inverters from a third-party supplier, and the HIP inverter from yet another vendor. These systems needed to communicate seamlessly, sharing data about engine speed, load demand, coolant temperature, and dozens of other parameters. In practice, communication protocols didn't always synchronize correctly. Locomotives would experience intermittent faults where one system would send data in a format that another system couldn't interpret, triggering protective shutdowns. An engine controller might report overheating even when temperatures were normal, causing the locomotive to derate power just as the train was accelerating from a station stop. Traction inverters would occasionally lose synchronization with the engine controller, causing abrupt power interruptions. These weren't hardware failures in the traditional sense. Components weren't breaking. The problems were software integration issues, and resolving them required extensive collaboration between EMD, Caterpillar, and the various subsystem suppliers. Engineers would identify a fault condition, trace it through the communication networks, determine which system was sending incorrect or ambiguous data, rewrite the relevant software modules, and then test the modified systems to ensure the fix didn't create new problems elsewhere. The HEP inverter presented its own challenges. During early summer testing, inverters would overheat during extended operation in 100+ degree weather, forcing the system to reduce HEP output. Passenger car air conditioning would degrade, leading to complaints from riders. The underlying issue was inadequate cooling for the inverter's power electronics. EMD redesigned the inverter cooling system, adding supplementary fans and improving coolant flow paths. But implementing the modifications across the fleet took months. Metrolink's maintenance crews faced a steep learning curve. The F125 was unlike any locomotive they had previously maintained. The C175 engine required different maintenance procedures than the 710 engines in the older F59PH fleet. Diagnostic procedures for the modular electronic systems were entirely new. Technicians needed training not just on the hardware, but on the diagnostic software used to interrogate the locomotive's various control systems. By 2017, Metrolink had lost patience. The agency publicly criticized EMD for the delays and reliability issues, and threatened to withhold payment on undelivered units. EMD responded by assigning additional engineering staff to resolve the outstanding problems and accelerating software updates. Gradually, the F125 fleet became more reliable. By 2020, most of the early teething problems had been resolved. Software had matured through dozens of revision cycles. Maintenance crews had developed expertise with the locomotive's unique systems. The C175 engine proved durable and fuel efficient, with specific fuel consumption figures better than the older 710 powered units, despite the substantial increase in power output. Today, the F125 is considered one of the cleanest passenger diesels operating in North America. The Tier 4 emissions controls work reliably, keeping nitrogen oxide and particulate emissions well below regulatory limits even in California's stringent air quality districts. The locomotive's acceleration performance exceeds that of any previous diesel commuter unit, allowing Metrolink to maintain aggressive schedules even with longer, heavier trains. The crash energy management structure has not yet been tested in a real-world collision, but FRA certification testing confirmed that the design meets or exceeds federal standards. The reliability debates continue. Some Metrolink personnel argue that the F125 is more complex than necessary, and that a simpler design would have been more cost-effective. Others point out that the locomotives are now meeting or exceeding availability targets, and that the complexity is the price of meeting modern emissions and safety standards. What's clear is that the F125's development highlighted the challenges of integrating cutting-edge technology into conservative industries. Railroads value proven reliability, and the F125 required an extensive proving period before it could earn that trust. The F125 was not a commercial success in the traditional sense. Metrolink remains the locomotive's only customer. Other commuter agencies considering new equipment during the same period chose the Siemens Charger instead, a diesel-electric unit powered by a Cummins QS K95 engine, which itself is a Marinese design adapted for rail service. The Charger succeeded where the F125 struggled primarily because Siemens brought a different approach to the North American market. Siemens had extensive experience building passenger locomotives for European railways, where diesel-electric designs are common. The company established a comprehensive parts and service network across the United States before the first Chargers entered service, ensuring that agencies wouldn't face the support challenges that plagued early F125 operations. The Charger also arrived later, benefiting from lessons learned during the F125's troubled introduction. Nevertheless, the F125 influenced the direction of North American passenger locomotive development. It proved that Tier 4 emissions compliance was achievable in a high-power diesel-electric locomotive, dispelling industry concerns that meeting the standards would require unacceptable compromises in performance or reliability. It demonstrated that crash energy management could be integrated into a production locomotive without creating an impractically heavy or expensive design. And it showed that non-traditional engine sources could work in locomotive applications, opening the door for manufacturers to source prime movers from outside the traditional locomotive engine builders. The F125's modular electronic architecture has become standard practice in newer locomotive designs. The principle of line-replaceable units, where entire subsystems can be swapped quickly rather than repaired in the field, is now incorporated into specifications for new passenger equipment across the industry. This approach reduces the skilled labor required for routine maintenance and minimizes out-of-service time, critical factors for commuter agencies operating intensive service patterns. The locomotive also influenced research into alternative fuels for commuter rail. The C175 engine can operate on renewable diesel, a fuel synthesized from biological feedstocks that offers substantially lower life cycle carbon emissions than petroleum diesel. Metrolink has conducted trials using renewable diesel in the F125 fleet, exploring whether commuter rail agencies can reduce their carbon footprint without transitioning to full electrification. These trials have shown that renewable diesel works effectively in the C175, with no modifications required to the engine or fuel system, suggesting a potential pathway for reducing emissions from existing diesel fleets. The F125 also represents a transitional technology. Battery electric and hydrogen fuel cell propulsion are increasingly viewed as the long-term future for non-electrified passenger rail. Several manufacturers are developing battery electric multiple units for commuter service, and hydrogen locomotives are undergoing testing in Europe and Asia. The F125, with its Tier 4 diesel engine and modest regenerative braking capability, sits between the old diesel-only designs and these future zero-emission technologies. Whether the F125 becomes a historical footnote or the beginning of a new design lineage remains uncertain. EMD has not marketed the design to other agencies, and the company's focus has shifted toward freight locomotives and locomotive modernization programs. The Siemens Charger has captured most of the North American passenger locomotive market, but the engineering lessons from the F125 program about emissions control, system integration, crash energy management, and the challenges of introducing innovative technology into conservative markets continue to shape how passenger locomotives are designed and deployed. The EMD F125 will never achieve the iconic status of the F7 or the legendary reputation of the SD-42. It wasn't built to become a classic. It was built to solve specific problems for a specific customer in a specific regulatory environment. What makes the F125 significant is that it represents a break from tradition at a time when the locomotive industry was largely focused on incremental improvements to proven designs. EMD could have attempted to modify the 710 engine for Tier 4 compliance, adding layers of aftertreatment and accepting the weight and complexity penalties. Instead, the company chose to adopt an engine from outside its traditional lineup, fundamentally changing the engineering identity that had defined EMD locomotives for 8 decades. That decision carried risks. It required resolving integration challenges that wouldn't have existed with a traditional EMD engine. It demanded new maintenance procedures and training. It created reliability problems that damaged EMD's reputation and delayed acceptance of the design. But it also produced a locomotive that met requirements which traditional approaches couldn't satisfy. Clean enough for California's air quality standards, powerful enough for demanding commuter service, and safe enough to protect crews during the worst-case collisions. The F125 proves that innovation in the locomotive industry is possible, but it also illustrates why such innovation is rare. Railroads are inherently conservative. They need equipment that works reliably for decades, maintainable by existing staff, compatible with existing infrastructure. The F125 challenged all of those expectations, and it paid a price in delayed acceptance and limited market adoption. Yet, 21 of these locomotives now operate daily across Southern California, moving tens of thousands of passengers through one of America's largest metropolitan regions. They accelerate faster, run cleaner, and offer better crew protection than the locomotives they replaced. They represent engineering choices that prioritized safety and emissions, compliance over familiarity and tradition. The future may belong to battery electric or hydrogen propulsion, but for now, the F125 stands as evidence that diesel-electric technology still has room for evolution, that manufacturers can adapt to stringent regulations without abandoning performance, and that sometimes the most significant engineering achievements are the ones that break with decades of established practice. This is the EMD F125, a modern experiment on American rails, powered by an engine from the world of mining trucks, designed to meet standards that didn't exist when its predecessors were built, and running today as proof that locomotive engineering continues to evolve.